self-supervised learning, right? And if you just think back, the motivation for that was to learn these representations, right? These models that take as input an image and give you some sort of vectorial representation. And you want that representation to simply be a representation that gives you, that encodes a lot of important information about the visual signal, right, that you input into it. Why do you want that? Because then, if you have some sort of compact representation that encodes a lot of the information encoded in that image, you're going to be able to do a lot of things. You're going to treat that as a tool, right? Like it's kind of like a hammer that you can use to apply to a bunch of nails, right? And I showed you a few of those kinds of downstream tasks that you might be interested in, like classification, object detection, segmentation, etc. And so now that we have that tool, I'm going to show you just a few examples. I'm going to give a few, like a brief kind of tour of a couple of ways that we can leverage these types of models for these downstream tasks. So this is going to be a bit more applied this time around. So yeah, so that was a bit of a preamble. This is a yet more kind of context setting, right? So all of us, very typically, when we have a downstream task, we attack it using a supervised learning approach, right? Because we have some tasks, it might be classification, object detection, something else, and we want to supervise that learning, right? We want to be able to have a model that's going to work well for this specific task. And so typically when we have like a lot of data, we can use it successfully to do things like pre-training, like I mentioned in the previous talks, using really big data sets like ImageNet, or if we're talking about text, using Common Crawl. And then, as I said, we typically fine-tune them, right? So as you remember, so fine-tuning basically is having some model that is already pre-trained on some task, for example, using self-supervision, and then you fine-tune it, so you kind of continue to modify the weights, this time using some new set of data, right, that's specific to your task of interest. Right, and these are just some examples of the types of fine-tuning, the types of downstream tasks you might be interested in. For example, object localization for different types of applications. So autonomous driving might be one of them. So the issue is, though, when you have these downstream tasks, I talked a lot about the opportunities and the challenges of having labels, right? And that doesn't stop when you have a downstream application. You still have to confront this issue of, I need to have labels for my tasks to do my supervision, and that's not trivial to collect. So just to give an example of why this might be hard, right? So say you have a kind of application where you have some user query. So let's say you have someone who, let's say you want to design a system where a user can see something that they want to buy, right? So maybe they want to buy this pair of flip-flops, and they want to figure out, where can I buy this online? Is there an online retailer that's going to be able to sell me this, something like this, right? So you might want to have a kind of application where a user can take a picture of what they have found, search through some online catalog, and then find something similar, right? So that's a very standard application. You can use this sort of tool right now. The thing is, you have to think that new items are coming up every day, right? So online retailers are constantly updating their catalogs. New items are constantly coming online. And this is happening basically every minute of every day, right? So how can you have a model that is able to continuously perform well on this task if the data is constantly shifting, right? So this is one reason why it's hard for you to kind of continuously collect the amount of data you need to train good models for these tasks. Another example is taken from social media. So let's imagine you're running a social media platform and you have certain policies, right? So content moderation policies, for example, that users have to kind of conform to, right? And let's say, for example, some user puts some content that's violating your policies. You want to be able to take some action, right? And very often you take some action using a model, right, to kind of detect content violation. So once again, so content policies, moderation policies can be changing on an arbitrary basis, right? And so you don't want to have to continuously retrain your model as these policies change. You want to be able to have some sort of approach to modify your model without requiring a ton of data. So rather than do what folks typically do, which is collect a large enough set of data for their task, there are different alternatives we can think of, right? So I'm going to talk today about applying two of these kinds of approaches. One is few-shot learning, and another is domain adaptation. Okay, so I think you'll hear probably a fair bit more about these two things, so few-shot learning and domain adaptation next week. So this will give you a bit of like a teaser of that sort of approach. Okay, so first I'm just gonna, so the agenda is that I'm just gonna discuss a little bit, what few-shot learning is, a very brief introduction, and then I'll talk through two examples of how you can use this for object detection tasks. I may not do the second one, I think we may not have time. And then I'll give another example of using domain adaptation. So few-shot learning. How many of you are familiar with the concept of few-shot learning? Okay, great. So I don't need to spend too much time on this slide. So if you remember from yesterday, supervised learning, you can think of it this way, especially if you're looking at an empirical risk minimization approach, if you want to use that, which is pretty much, I would say, the dominant paradigm. Then you collect your training set, right? Your set of n examples, as we saw yesterday. And then you compute this loss, right? Which is a loss per sample loss. So in few-shot learning, it's a very similar paradigm. You still want to use this type of loss function. However, the constraint is that you're not expecting to have a lot of examples to work with. Okay, so in typical few-shot learning scenarios, people consider that they may only be 1 or 5 or 10 examples, right? Examples or shots. And then if you don't have any examples whatsoever, then you get into the zero-shot learning domain. And so to address this issue, when you want to train a model but you have like very few samples, there are a few things we can do. So you can kind of augment your training data. So we see augmentation come here again. And the concept there, of course, is similar to what I was mentioning previously, which is that if you use an augmentation that's not going to change very much how you would label that image, then you can consider it just another example that you can throw into your training set. Okay? And another one is to generate prototype representations, and that's what I'll talk about in this example I'm going to show now, which is to say, I'm going to just use these few examples I have to create some kind of prototype representation in the same way I was describing prototypes yesterday in the case of clustering. And then I'm just going to use these prototypes to kind of represent whatever sort of space for my task that I want to do. So what I'm going to speak about, the kind of paradigm for few-shot learning I'm going to speak about is called episodic training. So this is just one of many different ways to do few-shot learning, right? In this case, this is a meta-learning approach where you want to learn how to learn with just a few examples, okay? So the way this works is you basically try to simulate a few-shot learning scenario. So you tell yourself, okay, at testing time, I'm going to have to take just a few examples and use that to train my model. So at training time, what I'm going to do is try to simulate a lot of different few-shot learning tasks, okay? And I'll describe a little bit how that works. So the example is sort of like what you see here. So you have, at training time, you train a sequence of training episodes. So you have a set of trainings, a sequence of training, and so you can consider it a sequence of learning steps. And so this is why this is called a meta-learning approach, because you're learning to learn via a sequence of learning steps, right? So you kind of have an inner loop where you're learning and an outer loop where you're sort of learning to learn. And so in this, if you think of an example for classification, you have one episode. So this is one sequence, one iteration of your training. And your episode is going to contain one query image and a bunch of support images. So you're going to have Z support images for each of L sample classes. So let's say you have a data set with 100 classes. What you're going to do is you're going to construct or simulate a training episode by sampling 5 classes, right, from the set of 100 classes you have. Then for each of these classes, you're going to select L support images. So you're going to say, okay, I have like 100 animals, for example. I'm going to choose 5 of them. Dog, cat, etc. And then for each of these, I'm going to choose L examples of that. So I'm going to choose 5 examples of a cat image and etc. Right? So this is going to give me some small training sets that I'm going to sample just from this larger training set. And so once you have that, you call that an episode. And then you're going to train this learner, this embedding function, to take this query image and these support images and learn a classifier based on that. And you're going to continue to do that. You're going to continue to sample your big training set. You're going to continue to create these subsets. You're going to continue to train on them. And then what you're going to do is you're going to learn an embedding through this process that if given a new episode, is going to be able to learn a classifier in this few-shot setting, right? That's kind of the motivation. Let me know if you have any questions, of course, as always. So that's like the backstory to few-shot learning. So let's see how this is applied in a few-shot object detection scenario. So here, the task is to train a detection model. So if you remember, object detection is the task, let's say, of taking in some input image, which we call the query, and producing bounding boxes. So for example, you see the green box there, for every object of interest that appears in that image. Okay, so that's like the task. And we want to do this with just having a few examples of the classes that we're interested in detecting. So as I mentioned before, the common paradigm that is very dominant for this task is to use episodic learning, where you have, in every episode of your training, you have a query image, and then you have a set of L-sampled classes and Z-support regions. Okay? So what you do is you follow this sort of high-level paradigm, right, at inference time, where you have your query image, you have your set of support images, you encode them using some encoder, and this encoder is typically a representation that was learned, for example, using self-supervision. Okay, so it's just a pre-trained network that has really good representations. As an output of that, you have a set of vectors, a set of embeddings, phi and phi prime. And then once you have these two, you throw them into some kind of similarity network that's just going to compute the similarity between the query and the support regions. Okay, so it's I think in that sense, it's pretty intuitive, right? So what you're going to basically do at the end is you're going to say, I have this query image, I have these examples of what I'm looking for, I'm going to just compute a similarity between regions of my query and these support examples of what I'm looking for. And when I find a close match, I'm going to say, okay, it's that category. So that's kind of the setup. So given that, I think it's pretty clear that one thing that's quite crucial here is indeed the similarity network, right? We can kind of take the encoding network for granted. This, once again, is where we really leverage the types of rich representations we already have, so we don't need to touch that much, if at all, right? So we're going to focus really on how do we compute the similarity. And so we have several options. We've talked a lot about computing similarities between features, right? So this is not going to be a surprise to anybody. So we can compute an inner product or a dot product or cosine similarity between different features, and that has some benefits, right? So you're not going to need to do any new parameters. If your similarity metric is literally just a dot product, it's very straightforward to implement. You don't need to train anything, which is great. That's actually a pretty strong advantage. But, I mean, it's relatively simplistic, right? We can do a lot more than that. What you can also do is to compute the inner product after you've done some other type of projection, right? So you can add, for example, another small neural network, right? So you can take your two sets of vectors, you can throw them into a new network, and that network is going to be able to compute a more rich similarity, okay? So for example, you can just add on top of it a multi-layer perceptron, and that's going to, if you train it well, right, it will be able to give you a more high-performing output. What's good about that is that adding on new weights, right, like new parameters, i.e. a new model, is going to give you a more expressive similarity metric. You're going to be able to learn to sort of better model your similarities. But that's going to introduce a lot of new parameters, right? And that's kind of a no-go for few-shot learning because, of course, as you know, to train this, you kind of need a lot of examples, and we don't have a lot of examples. That's going to be pretty hard. So what we're going to do is try to kind of get the best of both worlds, right? We're going to try to use kernels to give us a more expressive similarity metric than simply inner product. And the good thing with the kernelized representation is we're not going to need we're going to need basically no new parameters at all, right? So that's going to really be a nice middle ground between adding a bunch of new parameters or adding nothing at all, okay? And so this should ring a bell from the lectures you saw earlier with Professor Taylor, right? So he talked a bit about kernels and how they can be used to give you more expressive functions without adding new parameters. And this is exactly an application of that. So in our case, we're going to, in this work, what we did is that we leveraged different kernels to compute more expressive similarities, right? And we're going to look at 3 kernels, the linear kernel, which is actually sort of equivalent to the inner product, and also 2 other ones, a polynomial kernel and an RBF kernel. So an RBF kernel is sort of similar to what Professor Shaw-Taylor described as a Gaussian kernel, if you remember. It's going to operate in functionally the same way. So now that I talked a little bit high level, here is going into a little bit of more detail into the pipeline. So if you remember, we had the inputs, the query and the support. We had this encoding network, which we're not going to talk too much about. And then we had the similarity block. So this similarity block is now decomposed into a kernelization block and then a kind of relational block, right? And I'm just going to focus on the kernelization block, which is kind of the core of the work. So I'm just going to take you through each of the steps. So the encoding network, I won't talk too much about it. I'll simply say that it is a pre-trained ResNet 50 network. And so as I said, so this network is pre-trained. I think in our case, we pre-trained it. We might have pre-trained it. No, I think we did. We used a version that was trained using self-supervision, right? So this is where we get our really representative, powerful features. And I think in this case, we don't touch them. We don't even fine-tune. I think we just leave them. So that's just going to take us as input images and give us these nice performant representations. So these phi matrices, right? And so we have one set for the support regions. So you can think of these examples of your categories. And then we have a set for the query, the image that we want to try to label. And then we're going to put it into this kernelization block. And so the kernelization block, it has a few components. The first one is what is called a kernelized autocorrelation unit. And what that's going to do is it's going to take our representations that we got from the ResNet, right? So this is our phi representations, and then we're going to compute kernel matrices based on that. And we're going to compute it by applying the different types of kernel functions that we described, right? So I mentioned before we're going to use these. So each of these can be a row function that you see there, and you can plug in sort of whichever type of kernel you want, right? We're just using 2 of the typically most performant ones. But that's kind of arbitrary. It's just empirically chosen based on what we expect to work well, okay? So what that's going to give us is it's going to compute for us a matrix, okay? So a set of different types of matrices. And these matrices are going to be of dimension. So if you have a dimension, so you see here like the representations are of dimension D, okay? And so what you're going to get are these correlation matrices, right, where the correlations have been computed using these kernels. And it's going to be matrices of size D by D. Okay, so what this is doing is it's going from a D-dimensional representation to a D by D matrix, which you can vectorize and create a D by D dimensional vector. Okay, so you've really exploded the dimensionality of your representation. And this is going to give you a much richer representation, right? So it gives us what we kind of wanted, right? Which is to have a more complex similarity, to go beyond something as simple as an inner product, to give us a representation that's going to perform better. It's going to give us a better notion of similarity, which, as we said, is crucial for this task. Of course, the tricky thing, though, is that we now have a D by D vector, and that's huge, and it's going to be super computationally expensive. So we're going to have to find a way to sort that out. So what we've done in this work is take this D by D representation, right, which is very expressive, very performant, but it's going to be hard to work with computationally, and project it back into a new D-dimensional space. So that might seem weird, right? We went from D to D times D, now we're going back to D. So we're going to add something in between there that's going to make that make sense. Okay, so what we do is we do a kind of decorrelation of that space, right? So we have this D by D matrix. in this space, and we're going to decorrelate these the dimensions of this space such that the diagonal, so basically only D dimensions, will retain most of the information that's encoded in this matrix, okay? And we can do that using a kind of feature decorrelation approach that you see here, right? So what this is basically doing, it's saying, for this matrix, I'm going to compute the different eigenvalues of this matrix, and I'm going to only keep the D most important ones, right? I'm going to decorrelate it so that that makes sense. And then once I do that, I'm only going to keep the most, the dimensions that have the most concentrated information in them, okay? So that approach is going to allow us to go back into a D-dimensional space. But this is a new space. And this is a new space where the dimensions correlate to the most informative sort of regions of your space. And so we can kind of control how much decorrelation we want to do, because decorrelation might come with the cost of losing information. So we have to find a sweet spot between having a reduced representation, like going from D by D back to D, but not losing too much information in that process. Because you're not going to get it for free. You are going to lose some information, so you have to kind of control that parameter. And then also there's a power normalization approach, which I won't go into too much, but basically this is just another way to improve the information, to sort of like mitigate information loss, basically. It's just going to maintain a bit more information through that process of dimensionality reduction. Yep.
The eigenvalues that tell you what are the most important features when you do the spectral decomposition. Like, how do you actually segment the most important features from the ones that aren't? Yeah, how does the math work?
It'll just be the magnitude, so the eigenvalues, like how big they are. Yeah. So yeah. So the bigger the eigenvalue just means like the more variability there is in that parameter, so therefore the kind of more information that's stored there. Yeah, good question. Right, and just one point to note is that these parameters, you can kind of just control them manually by just searching through possible examples and figuring out what works well. We actually, in this case, use just a small predictor to predict like the best parameter to choose here. So rather than manually tuning it, we just sort of try to let the model learn a good parameter. And that's it. So that's it. I won't go into all the other stuff. I think that's kind of the key part, right? Because that approach is going to allow you, as I mentioned, as you notice there, right? So this approach didn't introduce any new layers. We have no new MLP layers. We have no new conv layers. We're simply just did this process of computing these correlation matrices, which requires no new parameters. You just compute the matrix similarities, and then you do some dimensionality reduction. And just that is going to, the results here, I won't go into it, but I'll just say that adding this new, let's say, kernelization, right, does improve performance pretty well on a lot of downstream tasks, right? So it's a good balance between making a more complex model and then making a more performant model. Okay, so that concludes this application of kernelized fusion object detection. So just to go through it again, right? So we saw that we don't have that many examples, and because we don't have that many examples, what can we do with the few that we have, right? So what we propose to do in that work is to introduce a kernel to give us a richer representation just based on the few examples that we have, and we saw that that does improve performance. So that's one way you can kind of tackle not having a ton of data. So in the interest of time, I won't go through the tensorized version. This is a very similar approach. It's just maybe using something you can consider a bit more powerful than the kernels we had before. And indeed, using more powerful approach gives you better results. So I won't go into it too much. So then now let's look at a kind of different way of addressing not having a ton of data, right? So now I'm going to go to this scenario where we have no new annotations. Okay, so what do we do in this case? So we have a model. We want to apply it to a new task, and we have data for the task. We have images, but we don't have labels, right? So what are we going to do? So let me talk through an example of that. So the example here is related to data distribution shifts. Okay, so just to kind of show what that looks like typically when you're doing machine learning, you expect something, a kind of flow like this. So you have a set of training data that you collected. Let's imagine, once again, you have a shop. You have a bunch of items you want to sell, right? So, and for example, you want to kind of automatically categorize them. So you you train a model to classify them using your typical supervised learning approach, and then you're going to deploy them and get different predictions for that data set. But in this case, as we've been mentioning, you've heard this from me and from other people, this paradigm assumes that the training data and the testing data has the same distribution. So you expect to see the same types of clothes or other items. But what happens if the data starts to shift, right? What happens if you start to get new items in your catalog with maybe different colors or completely different categories? What are you going to do in that scenario, right? And then this is going to continue to shift over time, right? So you can have, as time goes by, your data starts to look very different from when you first trained your model. And so domain adaptation is a set of techniques that have been proposed through many, many years, I guess decades by this point, to address what we call distribution shift, right? The shift in the distribution through some process. So these shifts there are kind of at least two ways that this can happen, right? So one can be a semantic shift, where you go from having one set of categories to a different set, so the semantic meaning of the categories is changing. So for example, in one case you might have dresses, in another case they may not be there anymore, you might have footwear instead, right? That's a semantic shift. But you can also have appearance space shifts, right? Maybe you still have the same types of items, but they don't look the same. So when you have these kinds of shifts, the kind of terminology we use is we say that we have a source domain. So we have the source domain where we've trained a model already, and then we have a target domain. So this is a new domain that we want to now apply the model to. And we may or may not have data for it. In this case, we don't. So to address that, to kind of adapt your model from the source to the target, you can either take an unsupervised approach or a supervised approach. And as I mentioned, we're going to do an unsupervised approach because we're not assuming we have any labels. Because as I mentioned earlier, labels aren't trivial to get, so it's very interesting to be able to kind of adapt your model without relying on new labels. So there's been a long series of work on unsupervised domain adaptation, and there are quite a few interesting surveys if you're interested. So what I'll simply say is that there are many approaches, both that don't use deep learning, right, that do things like kind of try to reweight the data that you have if you have a source data set, you try to figure out, okay, which images from my source data set are similar to the target, and you kind of try to retrain your data using that. There are many approaches you can use. And most recently, there started to be a lot of deep approaches too that do things like, for example, try to say, if I have a source data set and I have a target data set, I may not have labels for them, but what I do want at least is that the model, when it's processing the data, the output representations it gives you should be at least similar, right? So that's kind of one way you can try to approach this. So I'll talk about that in a bit more detail. So that type of approach, one such sub-approach in this space is called discrepancy minimization. So in this case, you have your two domains, right, ds and dt, and you want to learn this embedding function phi parameterized by theta. So you're going to optimize over theta. And that's going to transform your image into some kind of vector representation, right? And so what you want to do is you want to minimize this loss. So this loss is basically saying that this embedding function is going to take an image from the source domain and from the target domain, and it's going to, let's imagine you generated a bunch of these embeddings phi, right? You want the kind of expectation of that, so you want basically the average type of embedding you get from the source domain to be close to the average embedding you would get from the target domain, right? And what that's going to tell you is that even though I have these two sets of data, that they have some kind of shift, this model is going to do its best to represent them in a kind of similar way. And that's going to allow you to kind of address this domain shift. Right, and so I'm not going to go through this in too much detail, but this is just to say that one way you can actually apply this is in using the following type of network, where this network is going to embed both of these, is going to embed both source images and target images. And you're going to have a part of the network that's shared between the source and the target. And you're going to have a part of the network that is split. So you're going to have a network that's sort of dedicated to the source domain and another one that's dedicated to the target domain. And then what you're going to say is that once you have these outputs at the end, the set of source outputs and target outputs, you're going to apply this loss and use this loss to update the model such that the average source representation is close to the average target representation. So okay, that's kind of a general overview of unsupervised domain adaptation. Okay, so now we're going to talk about how we actually address it in a real application. Okay, so the application is once again, the example I gave you before, right, of having having like a consumer that's going to take a query image and then going to search for that item in a database of shop images, okay? And the goal is to try to find something that's a bit relevant to the query. So the domain shift here, there's a couple domain shifts, but the main domain shift here is what we would call a sensor shift. And this is actually quite challenging to tackle. So the sensor shift is the fact that when a consumer takes a query, they're normally taking it with a smartphone, which these days might be pretty good quality, but still, it doesn't really compare to the types of cameras that are used typically for online catalogs, right? And so not just how good the sensors are or how different the sensors are, but just also the composition of the images, the fact that maybe with consumers, people may not be wearing it, in shop images they may be. So there's a lot of differences between how items look online and how they look when somebody takes a picture of it in real life, right? And that's actually, that makes it hard to compare consumer images to online images. So that's one of the shifts we're going to try to address. So typically when you have this kind of cross-domain image retrieval, so we call this cross-domain because we have a source domain, which is a consumer image, and we have a target domain, which is online catalog. And so the task is going to be to try to retrieve some relevant item, right? And so what we're going to try to do is to learn an embedding such that we can just use a typical similarity metric, like a dot product, to try to retrieve similar items. Okay, so this should look super familiar for you. I showed a very similar slide yesterday, right? So as I mentioned yesterday, a lot of self-supervised learning approaches can be considered metric learning approaches. And you see that very much here because we're going to take basically the same approach. And so here what we're doing is we're saying, I want to learn an embedding function phi, parameterized by theta, where if I give it a training time a triplet, right? So it's going to get a query image, an image that's relevant, and an image that's not relevant. If I embed all three of them, in the resulting embedding space, the two similar images should be close together, so they should have a high similarity metric or a low distance, and both of them should be far from the non-relevant image, right? So that's what we're going to try to do. To do that, we need to collect these triplets and then basically throw them into some kind of loss function that's going to allow us to update the model, okay? So where the challenge comes in is that these cross-domain triplets are not going to be difficult and not going to be easy to obtain, right? Because of some of the reasons I mentioned before. So in practice, when you have a scenario like this, a real-world scenario, if you have a new shopping catalog, if you don't have labels, you're not going to be able to know what's relevant to my item and what's not relevant to my item, right? So you can't construct the triplets. And so, of course, you can decide I'm going to collect it, but we already mentioned we don't want to do that. It's very expensive to do to collect new data, so we want to try to avoid that. So what we're going to propose in this method is really how to address these missing triplets, right? How can we construct triplets when we have some data that's new and unlabeled, and then we have a source data set with some labels, okay? So what we're going to do is try to take a model that's trained on our source data and then adapt it to our target data set using a meta-domain adaptation approach. I'm going to describe what I mean by that. So to go through the whole problem space, right? So we have, once again, we have these shop images, we have consumer images, and there's the domain gap I mentioned before, right? The kind of sensor problem. And then let's say we have this new data set, right? So we have a bunch of shop images that came online, and then maybe they have some data associated with them. But then the consumer images, we don't have any consumer images, right? So we just got this new set of items, right, from our catalog, but nobody's bought it yet. Hello? Okay. Oh, that was fast. Thanks. Right, so you have this new target data set, and you're probably not going to have consumer images, at least initially. Right. So we're going to define the concept of a meta-domain as the set of all shop images. Okay? So rather than have your sort of source shop images and your target shop images, we're just going to say all images that are in a category are considered one big domain. And we're going to do the same thing. We're going to say we have this consumer domain, which is all the images that ever come from a consumer, right? And we're not going to think about the source data and the target data. We're going to focus just on the meta-domains, okay? So in this case, we're calling this meta-domain some high-level grouping of, for example, similar sensors, right? So shopping images and their appearance and that sort of appearance and consumer images will be considered different meta-domains. And so we're just going to focus on this meta-domain gap, and we're going to try to close that gap. So as we mentioned before, we don't have these consumer images here for the target, and so we can't really construct them as we would typically do, right? So we're going to adapt the source data set, as I mentioned, and we're going to approximate this domain gap by the meta-domain gap, okay? So to do that, we're going to have to find some way to associate these images with these images, right? So we're going to have to find a way to determine some kind of relationship between those two data sets. And so what we're going to do is we're going to take a pseudo-labeling approach based on clustering, right? We're going to basically find a way to cluster all the data together and propagate labels from labeled data to the unlabeled data. That's going to be the high-level picture. And then once we have those, once we propagate some labels, we're going to be able to construct these triplets, as you'll see. So just to try to visualize this, so once again, we have our shop images, our consumer images for the source data set. We have some shop images for the target data set. So what we're going to do, as you see here, we're going to kind of cluster them all. We're going to cluster all the shop images together, right? They're going to end up in different clusters. And then we're going to say, based on certain criteria, this is pretty ad hoc, it's just basically empirically chosen. When we see in a cluster where we have a lot of shop images that are sort of clustered together with a set of shop images from the source, we're going to say that basically you can consider them to be the same item, or at least you can consider them to be similar enough. And then if you have items that are outside of that cluster, you're going to consider them to be negative examples. And so once you do that, this means that you're going to be able to make a relationship between shop images, which you have, and positive examples, and then also negative examples, right? And so that's going to allow you to create these triplets that we were mentioning. So once we have these triplets, what do? We're going to use a triplet ranking loss. So this is kind of, I would consider it a flavor of a contrastive learning loss, basically. So what it's doing, if you look, it's basically saying, I'm going to compute the distance between my query image and my positive image. Okay? That's the first item there in the distance. And I'm going to compute the distance between the query image and the negative image, right? And this is just saying I'm going to encourage the distance between the similar items to be small and the distance between the dissimilar items to be large, right? So that's basically exactly what we were discussing yesterday about basically pushing similar things closer together and pushing dissimilar things farther apart. Right, and in our work, we used a bunch of different flavors of triplets. So we were able to continue to use triplets from the source image, and then we used these sort of cross-domain triplets as well. So we were able to mix shop images from the target with consumer images from the source, etc. Okay, so we have these, now that we have the model that's trained, right? So we have everything we need. We constructed triplets using this clustering approach. We use these triplets to train our ranking model, or you can consider it also just a similarity metric that we learned. And then now our model is done. So we just did some evaluations on this using two different fashion data sets. And maybe a few things to note here is that all of our proposed models used pre-training, right? So going back a bit to what we were discussing yesterday. So we never start from scratch if we can help it, right? So in this case, we took a model that was trained on our source data set, right? And then we adapted it as we were mentioning before. And so we call that source model DFBL for reasons. And then just to mention, so for clustering, we use a specific algorithm. I won't really go into it, but we just use a specific kind of hierarchical ranking clustering approach. Okay. So I'm just going to show you a couple examples of how this clustering works. So what we did is we had these two pairs of data sets, right? So we have a data set that was from one website, a data set from another website, and then we did this clustering approach. And so one website was sort of, you can consider DF, another one is S2S, these data sets. And what I'm just showing here is a couple examples of clustering across different data sets, right? Then you can see that these clusters are not the same item, but they're close enough that they allow you to kind of get a slightly better representation than you would if you were just using the source data alone. And that's just another example here. The idea here is just that, you know, the similarity that it's learning is kind of meaningful, right? The clusters that it's learning. And so I won't go into too much details into the quantitative results. I'll simply say that we tested this out, basically making comparisons between applying only the source data set, so not changing the source, not changing the source model at all, just taking the source model and applying it on your target data. That's one approach. And it's not going to be catastrophic, right? It will kind of perform to some degree, but it's not going to be as good as the kind of approaches we mentioned, right? And so another approach is to take the features, the pre-trained model, then apply a new layer on top, and just train that one layer. And that does improve performance a bit. And the way we train this layer is indeed using the triplets that I mentioned, these cross-domain triplets. And then the last approach is just to fine-tune the whole thing, right? So you have your pre-trained bits, you have your new layers, and then you fine-tune everything using these cross-domain triplets, okay? And as you progressively do that, you see performance improving. So it does show that having these new cross-domain triplets gives you some boost in performance. And yeah, I won't go into this too much, but it just says it also performs pretty well compared to some other approaches. And that's it. So in the end, I actually had a bit extra time, but I think it's okay. So just to recap, right? So we talked about what can we do once we have these powerful representations that we learned, for example, of using self-supervised learning. We can do different types of approaches to this. We can either use few-shot learning if we have limited data to train our target task, or we can use domain adaptation, okay? Then we went through a couple examples of using kernels to kind of make a more powerful representation, and then also to use some sort of domain adaptation. And that's it. I just want to thank my collaborators, and then I'm happy to take any questions. Yep. Is there a mic? I think he's looking for a mic. I can rephrase if needed. Or maybe you need to flip it on. I don't know if there's a...
Okay. So my question is related to the domain adaptation. So here, most of the examples we saw when we talked about the domain shift, it's mainly because of the system responsible for getting the data. So there is a domain shift because, so for instance, when we saw the images that they were quite very close to each other, but in the next one, when the new dress arrived, it was essentially from the same, it's similar, but the difference mostly is it's a new fashion, or probably kind of it's not previously seen, that kind of domain shift only. Now, if we extrapolate this to sort of like a robotics problem, for instance, so I'm sorry. So imagine this in terms of now, if you have a domain shift due to the morphology. So for instance, you have an animal showing a certain type of behavior. So you have the data, which is basically a behavior of a certain morphology coming from an animal. You want to replicate that kind of behavior on a robot that has a similar morphology, but not exactly the same. Do you think that the domain adaptation that you showed here, or the approaches you showed here, could be extrapolated to a regression problem tailored specifically for regression problems, of course, can be extrapolated for this kind of scenarios where we have imagine this like a elephant trunk, and it's showing some sort of behavior, and you want to replicate that on a similar robot with virtually infinite degrees of freedom, but showing similar behavior but not exactly the same morphology. So do you think it can be extrapolated to it?
It all depends on how similar you can get, right? So I know there's been work in robotics looking at different morphologies in the sense of, for example, let's say I have a bipedal robot and I want to be able to apply to like a different bipedal robot, but maybe, you know, the actuators are somehow a bit different, etc. Like, if you can get close enough, right, then I think this is possible, but I think it's a bit hard to know a priori, like how similar do you need to get for this to work, right? So I think something as simple as if you have an actuator for a robot and it's just not going to have the same amount of torque, so it's not going to be able to move as quickly or something like that, then the kinds of actions that you might learn in one may not apply to the other. So I think it's very nuanced, like whether you're going to be able to transfer. In this case, what is helping this method a lot is the fact that you do have this meta domain, right? So the shift that you need to kind of really focus on here is we're taking like a shortcut, right? Because basically we're saying, that what we really care about in the target task is solving this problem, right? So we have a shop image and we want to apply it to these consumer images. But we don't have this, so we're going to try to use the model that was learned here to solve that task. And then we're going to try to make the bridge between the two via the shop images. So we're going to try to say what's similar here to here. If we find examples of what's similar on top, we can use that to find examples of what's similar there, right? So what we're trying to do with clustering is basically try to find similar things between that and that, between the source and the target shop images. And that's not that hard, right? So if you looked here, this is one shop data set and this is another one, right? And of course they're different in a lot of ways, but fundamentally the images are not that different, right? So it's relatively easy for you to figure out, okay, it's not quite the same data set, but you do have items that look kind of the same. And then you can bridge that gap. In your case though, it may not be that you can find this kind of gap, this kind of bridge to the gap that you have. So it might be a bit trickier. Any other questions? Yeah.
I was trying to do without it, but yeah, that's why. You said a lot that you were using pre-trained network, and that it is. So my question is, what we can do to try to pre-train this network better?
Yeah, so definitely you can try to kind of boost performance a bit by pre-training it on something that's a bit more relevant to the domain. So for example, in this case, we took a model, we did a bunch of steps, right? So we took a model that was initially pre-trained using ImageNet data, which is a very rich data set, and it probably has images like this somewhere, but it's not quite the same domain, right? Then we took that data set that was pre-trained on, that model that was pre-trained on ImageNet, and then we trained it on a source data set, right? So we trained it on, well, let me use like a more, and then we trained it on this data set. And this data set's not like a billion images, but it's not bad either, right? So then we kind of adjusted it to the domain of sort of like consumer items, right? And then when we have that, we adapted it once again to our new target data set using kind of the pseudo-labeling approach I mentioned. So that's the kind of typical thing that you can do. Basically try to get as close as you can to your domain. And so practically speaking, what you would do here is you would take a model that was trained on a lot of data, a lot of generic data, and then you would fine-tune it on as much data as you can get from your actual domain, right? That's going to give you 2 chances to kind of boost your performance. And you could tell yourself, why would I even bother with ImageNet? Maybe I just pre-train directly on some huge data set of consumer images, and it might work. It's the kind of thing that very often, even just training on something that's not related, but still very rich in terms of the variety of the data you see, it can give you a boost in any case. But it's the kind of thing you need to determine experimentally. You just sort of empirically try different things and see what combination of pre-training works. Any other questions? All right. If not, then thanks so much for making it through these 3 lectures. And yeah, enjoy your lunch. Enjoy the rest of the seminar.